Good morning, good afternoon, and good evening, everyone. Thanks for joining us for another Data Engineers Lunch and starting your week with us. We appreciate it. I'm just going to breeze through some housekeeping items and we'll go ahead and get started. Our speaker this afternoon is going to be Obi, because he's going to be going through machine learning orchestration with Airflow. Really excited for that topic. Organizers for this event are Raul or myself. We are looking for speakers and sponsors for this event, so if you're interested in either opportunity, please reach out to me at the email listed below. We are a part of a larger community called Data Community DC, which believes in building an inclusive environment. So no matter your race, gender, or sexual orientation, everyone is welcome, and I expect respect to be given to all. Data Community DC is made up of a lot of different groups, generally all surrounding data. You can find out more about these groups at the links listed below. So what do we cover here? On this lunch, we cover everything from the ingress and egress of data and everything in between. We cover everything from databases, ETL, data wrangling, and all the tools and processes in the data engineering world. If it's your first time joining us, welcome. Please leave your name, how you work with data, how you heard about this lunch, and some topics you'd like to hear about in the future. Group rules: if you have a question, do ask it. Obi doesn't mind if questions are asked during the duration of the presentation. So whenever you have a question, just go ahead and drop it in the chat. Like I mentioned, please be polite and courteous to others. And we are trying to build a community, so do share what you know with us. Here at Anant, we build and manage global real-time data and analytics platforms surrounding Cassandra, Spark, and Kafka. We'd like to thank our program sponsors, our organizational sponsors, all listed below. And then very quickly, if you have any announcements, any jobs, meetups, hackathons, conferences, classes, please go ahead and leave that in the chat with a short description and any related links. Want to bring your attention to our events coming up. We always have our Data Engineers Lunch on Mondays. We usually have our Cassandra lunches on Thursdays at noon. But this week, we're going to be having a special talk on automating your job and businesses with ChatGPT. That is going to be on the 8th, which is a Wednesday at a different time. So the same great knowledge, just a different time slot. So we ask our Cassandra Lunch members to join us for a special lunch on Wednesday. We'll have a lot of notifications coming out about that in the coming week, coming next few days. So keep your eyes on our socials. If you haven't already, please subscribe to this channel. And then finally, our runbook is available for one more week. If you haven't gotten this edition yet, please go ahead and download it. I'll be leaving a link in the chat. It is free. And with that, I'll go ahead and hand it over for our speaker today. Over to you, Obi.
All right, thanks, Auckland. Sharing my screen. All right, so as you heard, my name is Obioma Anomnachi. I'm an engineer here at Anant. Today's topic, we're going to be talking about machine learning orchestration with Airflow. We're actually going to extend that and talk a little about MLOps at the end. Because today's topic doesn't have a demo associated with it, feel free to just drop questions or comments in chat whenever, and I'll relay them to me if you have questions. All right, so getting started at the very beginning, what is Airflow? We tend to talk about Airflow a lot, especially in relation to this lunch and our Cassandra lunch, because it's our chosen tool here at Anant for workflow scheduling. And that's what Airflow does. It's good for automating and scheduling repeated processes. You write up your workflows in Python, break them down into individual tasks that get defined in that Python code, but you're not actually limited to just Python. So the main two operators in Airflow are Python operator and Bash operator, but providers include operators for all sorts of external tools, things like Spark, Hadoop, as you can see in the lower right there. All sorts of external tools that are very useful. You define dependencies between the tasks in order to create a workflow from them, and they have to be directed acyclic graphs of tasks. So we talked about DAGs a couple of times in these lunches as well, talking about other ETL tools that also use the concept. The idea is that your tasks can depend on one another, but they cannot, there's no cycle, so they cannot ultimately depend on the results themselves. You can use Airflow to schedule these workflows or to execute them manually, starting from the beginning and going to the end, or schedule them to run every so often. Airflow You can use cron syntax to define the schedules, but Airflow also includes tags for common frequencies like daily, weekly, monthly, etc. You can monitor individual task progress, DAG progress, and view logs in the Airflow UI. So how does that apply to machine learning? So when we talk about machine learning, we're generally talking about the training process, which is sort of a straightforward pipeline. Machine learning processes always get broken down into smaller chunks, and most of those end up being batch processing. There are ways to do machine learning in real time with streaming and stuff like that. But most of the time when you're talking about machine learning, you're talking about you have a chunk of data that you need to do something with, whether that's the pre-processing, whether that's the training, and all of that has to happen at once. Even your predictions, which theoretically, when you envision that, that's like one request comes in, the model makes a prediction, you give that back. You can make predictions in batches, especially if the results aren't time sensitive. If you're doing something like analytics on your data that's sitting there and not going anywhere, sometimes you can feed that into your model in batches and get your results back all at once and push them into wherever the store is for those results. But basically, this structure of small individual tasks that rely on each other lines up well with Airflow's ability to schedule, automate, and manage dependencies for tasks, to create workflows and manage them. The main sections when we're talking about ML pipelines are data pre-processing, model training, and deployment. This image is broken down into 4, and we will talk about all 4 of these sections, but a lot of the time we talk about split and we talk about data preparation in the same breath, because it's really all preparing your data to be used with your selected machine learning model. All right, so step 1 in that process, data preparation. It covers a whole bunch of discrete data transformations that you use to bring your raw data in line with the needs of your model. Basically, it's a set of ETL jobs. Different models require your data to be in different forms. So starting from your raw data, you might actually be storing 3 or 4 sets of data that are more in line with each of the different models you want to train. So this is something about Airflow generally. You want to keep all of your actual data processing separate from your DAG code. It's just like good practice, really. Because if your code, basically Airflow, the system has to actually run your code in order to extract the DAG object from it, to be able to manage that workflow. And if when you run that code, that Python file, in order to extract that object, if Python is stuck actually doing data processing there, it's going to bog down your scheduler, your worker processes. Basically, Airflow is going to slow down. So it's best to start separate processes out on other systems, maybe on other computers, or potentially in systems like Spark or Hadoop, in order to manage these actual processes. So when we're talking about data preparation, we're talking about things like null removal, data imputation for missing data, scaling and shifting to make sure all your numbers are in line, potentially even stuff that is sort of like its own model, like PCA or other component analysis. But basically, you have your data somewhere in its raw form. You want to take that data in, you want to transform it, and you get something closer to data that can be used with your model. And one of the things about Airflow that is sort of a holdup in this process is that Airflow doesn't like you to pass data back and forth between tasks. Basically, there is a method for that in Airflow called XComs, but that's meant for smaller portions of data. So if you're doing big data processing, you'll want to have external places to store that. Question came in. I'm more interested in spending some more time discussing the architecture slide on the slide before the data prep slide. Okay, so this pipeline. Yeah. So I've actually talked about this previously in machine learning with Spark and Cassandra. There's a series where we break these down in like very specific detail. But basically right now we're just in the first block, preparation. We take our raw data, and what we want out of this is data that's suitable for the machine learning algorithm. It says features and labels, but that's not really all that you need. So depending on what model you're going on, you might not even need something like labels. But turning raw data into features is something that every machine learning algorithm is going to have to grapple with. The second section here is called split. So once you have your data, you can't just train your model on it and say, I'm done. So instead, in preparation for the actual training and then further steps down the line, tuning, estimation, validation, you split your existing data into sections, because you can't test on your training set and you can't validate on your test set. So you need to split your existing data into sections. The bulk of it gets used to train your model. Some of it is held out to test the performance later on and to validate as well. And then you go into the training step where you actually train your machine learning model. You feed in the training set into the machine learning algorithm and you get out the model. And you can't use that as is. You test or validate depending on what you're actually doing. So the validation set is for parameter tuning, really, and then the testing set is for performance estimation. And a lot of the time, those processes actually send you back to the start of the training step. And as well, sometimes the way that you split your data, which we'll talk about a little bit later, is more complicated than static training set, static test set, static validation set. And that also interacts with how you actually need to be able to train your model and deal with that feedback. And then once you have your model, you take your final model and you put it out in production somewhere where it can actually do the work it's supposed to do. So this one talks about predictions because it's talking about supervised learning where you have labels in your original data. So when you feed in new data, what you get out is a label for that data, even though you don't know it necessarily coming in. And being able to service those requests is what that section is all about. Okay, so we basically covered what I had to say about data preparation. There are things here that can even involve training other ML models. Like in one of our data pre-processing talks a while ago, I talked about ML imputation, where you train an entirely different predictive model to fill in blanks in your data that you already have in hopes of getting more data to train your actual model with. But you do have to watch out when you're doing things like that because eventually it might shift things about your data. If you're shifting the statistics of your data, you're going to get out a different model and you may not be shifting it in the way that gets you more accurate predictions. All right, the train test split. Like I said, mostly this gets lumped in with data pre-processing. It involves randomly splitting up your data in preparation for model training. What you really want to estimate when you're testing the performance of your model is how accurate it's going to be on new data that comes in for prediction. But obviously you can't test that because you can't test that directly because when data comes in for prediction, it specifically is lacking the label that they want you to predict. So there's nothing to check against afterwards. So instead what you do is you hold out some of your data for testing by randomly splitting your full data set into pieces. And in order to determine the performance of our model, we test it on data that we know the real label for. So we have this entire set of data that we know the label for, and we split that into train and test sets. That is at least the standard model for doing this. But if you look at the sort of chart below here, this is actually a demonstration of a more complicated method called k-fold cross-validation. Basically, you split your data here into 5 sections. and then designate one of those sections as test data, and then the rest of your data set as training data. And then each section gets its turn to be the test data, and you train and evaluate your models on each of those sets so that you can make sure that, one, you're not training a model and then testing its performance on that same data that you trained on, which is not a good way to estimate performance of your model, since it's just spitting out the data that was put in. Not to say that every model can perfectly reflect your training data, but it's going to have inflated performance on data that it was trained on compared to data that it was not specifically trained on. I forgot the second thing that I was going to say. So in terms of scheduling and management with Airflow, this split, obviously, if there's more data that comes in, you can't just add it all to the training set or add it all to the test set. So you redo the split entirely when new data comes in. There is also something called time series cross-validation, where basically as new blocks of data come in, let's say your data is split into blocks of months. As new data comes in, that gets designated as a test set, and all the old data is added to the training set. That's a potential way to do it if you keep accumulating data over time. But basically, because this split needs to be redone, and the data processing obviously needs to be redone when you get in new data, Airflow scheduling for these tasks is generally pretty efficient. So if you have, say, a Spark process that does your data pre-processing, and you schedule that in Airflow with a monthly tag, then every month when your new data comes into whatever it comes in, your Airflow task will take it up and make sure that that data is ready for machine learning, or make sure that your data is split up into pieces ready for machine learning. So we can move on to the model training stage. The majority of machine learning algorithms, model training is just, your standard batch process. It starts, you train your model on all the data. It gives you back the model object. Oh, another comment. Significantly inflated performance. The data science book will fall on you from a huge height if you. Yes. If you use your training data to inflate your test results, your data science professor will throw something at you. Yeah, so usually when you're training a machine learning algorithm, it's not really usable until your training is fully complete. And then, your testing is done and you're able to confirm that it's complete and it has high enough performance for you to actually use. Not every model is actually like this. There are plenty of models that you can, train on some subset of data and then look at them and test them and use them. And then later you train them on more data from that starting point, and you're able to continue using that over and over again. So basically your model is able to improve over time without being replaced. All of the previous training is still in effect, and it just has to be exposed to new labeled data in order to continue getting better. So there are two types sort of architectures. I'm not really sure what the word is here. Two methods for how to service requests with machine learning models. The first is a permanent model sort of method where you train your model and then you put that model somewhere, usually called a model registry. And then when new prediction requests come in, you use whatever model is the most recent in your model registry, or you have some scheme to pick a model from a model registry depending on what's in the request. So you train your model and then you save that to a central location. And then that's contrasted with transient model methods, where when a request comes in, that triggers the training process. And then the model that results from that training process is used to service the request, but is then thrown out. If your data changes too fast, and models that are stored around for even, say, a day or something like that, are basically useless to any future predictions, then you sets you up to use a transient model method. Whereas permanent model methods, if your old models still have some use, like you can use them to get an idea of where to start your parameters for the new model, or you can use them to service specific requests that still come in. There are advantages to having all your models saved in a model registry, especially if, say, you get in a new batch of data and it throws everything off for a certain subset of predictions. You'll want to still run those on the old models while having the new requests that still work perfectly and are improved in performance with your newer models to use those newer models. So there are a number of ways to run a model registry as well. There are a lot of tools and services available for this. But one thing that you can do potentially, if your models are in Python, if you're using something like sklearn or TensorFlow, basically all Python objects can be saved to disk using pickling. You could, I never finished that line. Anyway, if you have models that are small enough, you can potentially just put them into the Airflow XComs and load them out in the next task down the line. This isn't always a good idea. Like I said, XComs are sort of size dependent. You don't want to put anything too big in them. But yeah, that's the contrasting model training. There are tons and tons of machine learning models, and a lot of them behave differently. But this step is generally pretty standardized. If you're using like scikit-learn or Spark MLlib, you will have your model object, and then when you want to train it, you will feed it the data set to the fit method, and then when you want to use it to classify or predict new data that comes in, you will use the .predict method, and because of that standardization, it's pretty easy to compare different models. So you can even do this model training step where you train a bunch of different models on the same data, and then you pick out the ones that are the best, or maybe you store all of them. Then once you have all your models, potentially in a registry, potentially just being passed to the next task in the line to do the prediction, this is where you're in deployment. You deploy your machine learning model to serve predictions on inputs that are not part of the original data set. So neither the training, nor the testing, nor the validation set. It is technically possible to have Airflow answer these requests. You can use the Airflow API to run tasks and give back the answers. But Airflow isn't really meant for that. It's better to use Airflow to keep your models up to date in some external system. If you start a web server with like Flask or something like that, and pass it your model. Or you can even, again, use something like Spark or other ETL tools that we talked about to use your model to do batch processing on large chunks of data at once. And that could potentially be scheduled via Airflow. And then if individual requests are coming in and require service immediately, better to not have Airflow manage that, at least not at the lowest level. So what we've been talking about today is part of MLOps. So the machine learning training process is not the whole thing. It's just a part of the wider field of MLOps, or machine learning operations. So when we talk about machine learning operations, that's everything that we talked about today plus extra stuff. Three main phases, if you're talking about MLOps, are design. That's mostly done manually. Understanding of the business use case, you have to analyze. Another question, when you talk about the storage of the model, do you mean specific values for the weights for different variables? So it depends on what machine learning model you're actually using. So if it's a neural net, that is a store for all the weights of the neurons within that model. But if you're using something like SVM, it's the location of all of these support vectors and stuff in your feature space. Basically, models store their internal parameters in all sorts of different ways. But not all of that is actually important. So what's important is the ability to store those things and then bring them back into the system later on. So when you store a neural network, depending on what file format you're using, it's possible that you're storing the entire Python object with all the weights and everything else in there. But it's possible that, you know, it's just some mathematical representation of all of your neurons, or it's possible that it's shorthand for all those things in order to build back your neural net later when you try and load it into a different system. And I talked briefly about storage models for machine learning models in a different talk, but basically not all of them even store them the same way. So you can talk about, if you pickle an object for a neural net, that's a Python specific implementation, you save it from Python, you can only load it from Python. But there are also intermediate formats that store the weights and stuff like that, that you can use to potentially load this same neural net with the same weights and therefore the same like predictive performance into a different language or a different system altogether. All right. So the design part of MLOps is about understanding the business use case, understanding what data and tools you have available, and understanding the structure of the software that's going to actually, you know, perform the process later on. So this could potentially also include some statistical analysis of your data, even data science experiments. And that sort of goes into the next section of model development as well. But basically, if you have your data scientists with Jupyter notebooks open, running, creating models and checking them and looking at what your data actually allows and that sort of stuff, that's part design, part development. But when we talk about development in MLOps, that's all of your data engineering for your pre-processing steps, your model selection tests, your parameter tuning, all sorts of things that will go into creating the actual model from your data. And then when we talk about operations, that's your ability to deliver models to production and to be able to continue to deliver them over time. So when we talk about operations, we talk about not only the deployment of your model, but also CI/CD for your model generation code, your data management, what triggers new builds of your model, the monitoring of your performance of your model over time, things like that. And there is this graphic that does a pretty good job talking about MLOps. So starting, I guess, at the end, where you have your machine learning prediction service, that goes into data monitoring, where that goes into performance monitoring, where data that comes in, anything that you know the label of, gets like monitored over time, so you can tell when your whatever validation metric you're actually using, in this case, let's say F1 score, since that's pretty commonly used to monitor the performance of your service on data, whether that's old data, new data. If that performance degrades over time with new data coming in, then you should have that once it reaches a threshold that of acceptability to your process, that should trigger a new build of your model, because you don't want to keep using your model even as it degrades potentially to chance or worse. You want to train a new one that's going to be actually useful. And this also goes into data analysis that you can use to run data science experiments, including model analysis And then that code goes into your source repository, which CI/CD manages. And that includes both your data engineering pipeline to get your data pre-processed and your actual ML model engineering. So when we talk about, there's this section here, ML metadata store, that looks a little bit disconnected, but that's talking about stuff like default parameters and stuff like that, which can change over time, but don't necessarily get stored in your code that's up for CI/CD. And so your regular data goes into a feature store after it's been pre-processed and then fed into your model engineering. And once you have your model, that goes into your model registry. And then however you choose to serve your model, coming out of that model registry and picking the correct model to be able to deploy that prediction service. So it is kind of cyclical, but there are all of these regular processes that either depend on one another. Like you can't do your ML model engineering if your previous data engineering hasn't been done, or need to be run on a specific schedule, like your performance monitoring that monitors change in the performance of your model over time. You need to be able to run that daily or weekly or even hourly in order to keep track of when you should actually be triggering that new automated build. So even if all of these individual pieces could be automated, if they weren't tied together properly, you'd end up with a service that would just be spitting out new models whenever, and they wouldn't necessarily be trained to the highest standards or, even necessarily acceptable in terms of whatever performance monitoring you might put into place. All right. So seeing my prepared slide deck, I have a little more material to go over, but now is a good time if anyone has more questions to also put those in the chat. Okay, so this is from mlops.org. It's an organization that keeps track of information regarding MLOps. So one of the things that they say about MLOps is that it should be language, framework, platform, and infrastructure agnostic. So in order to pick what goes into your specific stack, there are all these sort of considerations that need to be brought into account. So we talk about data analysis tools, experimentation. I said Jupyter notebooks could be used for data science experimentation, but obviously that's not the only thing. There's your actual code repository. And the previous graphic brought up how CI/CD is important to make sure that updates by your developers to the source repository actually get down to the area where they're doing the actual model engineering. There's your ML pipeline training, your model registry potentially. Like I said, if you're using a transient model sort of framework, then that's not really where this would go. Your model serving and monitoring tools. So basically you can fill all these in with a huge number of different things. And here is an example, data analysis with Python and pandas. I mentioned Spark. There are lots of other tools. Source control with Git, potentially used for CI/CD. Test and build services with PyTest and Make. So this is something that I didn't actually mention because it's not in this graphic, but lots of areas in MLOps also demand certain types of testing. So it's not just the performance monitoring for your model, but also testing in the source repository that you're not going to push broken code out into the data engineering or model engineering pipelines of your data analysis, stuff like that, of your model registry, even that you're not throwing away completed models. So all sorts of these things have testing, and there are ways to manage that inside the framework of MLOps as well. Talking about deployment services, model registries, data set registries. So something more than, I believe we actually had a talk from a data set management like company a little while back, but basically keeping in mind the data sets that each model is trained on. Maybe you want to have different versions stored in different places to see if you can train a better model on the same data in comparison to a model that you already have. You don't want to potentially only keep your single updating data set, because that might affect your ability to go back and do experiments on old old code or old data sets, old code, old versions of your model, etc. Feature stores, ML metadata stores, pipeline orchestrators. So pipeline orchestrator in this case might be something like Airflow. And then there is also this Linux Foundation's LFAI visualization of lots of different AI and MLOps tools. So when we talk about data analysis tools, come on. Talk about all sorts of things. So these have their own projects that they're incubating or have incubated associated with this foundation specifically, but also, let's zoom in a bit more. You can see things like Apache Mesos or Spark here, lots of different distributed computing tools for that data processing step. When we talk about workflow management, we've been talking about Airflow, but obviously if you wanted to use Argo, which we talked about as an ETL tool at one time, or Luigi, which is also something that we've talked about here, Prefect, so that you have options for basically every tool in this workflow. Like they said, it's language agnostic, but it's also framework and platform agnostic. So if you wanted to do this on Google Cloud, there are tools for that. If you want to do this on AWS, if you wanted to do it locally. And then at the top here is about the machine learning stuff specifically. So we talk about all these ML platforms, as well as individual ML libraries. There's scikit-learn, but also tools for things that they kind of fall under machine learning. So deep learning is for basically large neural networks. There are lots and lots of tools out there to manage that because probably not something you can do on your individual computer and have it count as deep learning. Reinforcement learning is an entirely different set from supervised and unsupervised learning, but it's something that you might need to do. So you can have it managed through all these different platforms, and then your manual programming tools as well. We talked about workflow and pipeline management. Data governance is a thing that you might need to keep track of. Labeling and annotation. So if your data is unlabeled and needs to be labeled for you to do your machine learning task, these are all tools that can help with that. Stream processing. So there's all sorts of these tools, and like it says here, you kind of want to fill them in based on the requirements of your platform. So if you're doing really heavy data analysis, then you probably can't really use Python and Pandas on a single computer to get that done. You might need to switch to something like Mesos or Spark in order to be able to do that in a timely manner and get that data to your ML pipeline. And then there's also this called Awesome Production Machine Learning, talking about all sorts of tools for doing all sorts of things. If you're talking about the security of your ML models, if you're talking about neural search, including stream processing and stuff like that, which we hadn't really covered in this talk. Because like I said, a lot of machine learning processes are batch processes. But if we're talking about modeling, so there was a question earlier as well about storage of the models, right? So this is a bunch of tools for helping with that. So I actually talked about ONNX briefly. It's a tool specifically for storing neural nets, but it's language agnostic. So you take your neural nets and this basically transforms them into weights and stores them. And then there are tools that can load that into, say, PyTorch, or load that into sklearn as a neural net, or load that into other tools, other languages, basically to let you use that model even if you're outside of the language that it was trained in. But also, like I said, not all models are like this. You can turn a neural net into a set of weights, but you can't necessarily turn, say, a decision tree or a random forest into a set of weights to store in that same format. But there are ways to store them as well so that you can load them in later and, you know, make predictions on that model without having to retrain it every time. All right, that is about all I have today. So if there are more questions, I can think about answering them. But otherwise, that will be it for me today.
Thank you, Obi. Let's give people a couple minutes, see if any more questions come in. I don't see any at the moment, but just some housekeeping items. Again, we do have that special lunch coming this week on Wednesday at 1 p.m. Eastern. It's a little bit later, about an hour from our usual lunches. We do ask you to check our events page and register if you haven't already. And otherwise, so we won't be meeting for our Cassandra lunch next week, but we will have another data engineers lunch. I want to thank you, Obi, for another fantastic talk, and thank everyone for starting the week with us. And we'll see everyone same place, same time next week. Thanks, everyone. Take it easy.